We'll wait one more minute and then we'll start. So you can go ahead and share your screen if you want.
Yeah.
All right, so welcome everybody back to the Western Hemisphere Colloquium on Geometry and Physics. And today we're going to start a new occasional type of series, sub-series in this seminar, which is What Is, where a speaker will explain some concept or idea or topic of current interest from a general point of view. And today we're very pleased to have Ciprian Manolescu from Stanford University, who will tell us what is Floer homotopy. Ciprian.
Okay, thank you very much for the invitation. I figured I would talk about Floer homotopy, which is the theme of the current MSRI program that I'm organizing with a bunch of other people. And this is the plan of the talk. I will start by reviewing Morse homology and Floer homology, the different versions that we have in symplectic and low-dimensional topology. Then I will explain what we want to do in Floer homotopy. And then I will talk about how it was done, different constructions of that. And then finally, I will mention a few applications. All right, let's start with Morse homology. That's a classical subject. The simplest version is when we have a compact and smooth manifold closed without boundary and a Morse-Smale function on it. Then we make a complex made of chain groups generated by the critical points of F, and the differential is going to count with some signs the number of gradient flow lines from X to Y. And it's well known that the homology of that is the homology of the manifold itself. That's in the case that M is closed, but what if M is non-compact? This is perhaps slightly less known. So in that case, you can still define Morse homology, but we need some condition. Let's look at S being the set of all points on gradient flow lines between two critical points. And let's assume that S is compact. Okay, so that in particular implies that we have finitely many critical points. And then we're also going, so this set S is going to have these critical points and also everything that's on flow lines between them. There may be other flow lines, like going from infinity to infinity or to a critical point. We don't care about them. We just care about this set here. And well, sometimes it's compact. If it is compact, then the usual proof that this is a chain complex works, and there are finitely many critical points, flow lines between X and Y. And then what do we get for the homology? We can make CK as before, and then the homology of CK is the homology of the reduced homology of the Conley index of this set, which is basically, let's see, what colors should I use? It's some suitable neighborhood of S, which we can take to be some manifold with boundary. And then on its boundary, we're going to look just at the set of the exit set. So the parts on the boundary where the flow exits as opposed to entering. So L is the exit set. And yes, Morse homology is the homology of N relative to L, because basically you're attaching cells to L to build N by Morse theory. All right, so I'm going to come back to the Conley index later. Let's just remember that that's what it is. When M is closed, the Conley index is just N divided by the empty set. It's just M, the whole thing divided by the empty set. All right, so Morse homology is the model for Floer homologies. What is Floer homology? Well, it's Morse homology in infinite dimensions. You typically have some Banach manifold, and I don't need you, Siri. How do we stop you? I don't know. Okay.
I don't have an answer for that. Is there something else I can help with?
No.
Okay.
Sorry. Let me try again. Okay, we have a Banach manifold and a functional on this Banach manifold, and we have critical points. And now the Hessian of F, so before it was splitting into, we're assuming it's non-degenerate, and before it was splitting into positive and negative eigenspaces. So A plus is the direct sum of positive eigenspaces of the Hessian and of the Hessian, and D minus, sorry, let me try again. The Hessian gives a decomposition of the tangent space to B into these. And now they're not finite dimensional. We want them to be both infinite dimensional. So the indices are infinite, but we can still typically define, well, in good cases, we can still define sometimes. Let me put it like this. Sometimes can still define, well, the relative grading between two critical points as opposed to absolute grading. Sometimes you can make it an absolute grading with some tricks. And from here you get the complex CK, and you take homology, and you get what's called Floer homology. Okay, in good cases, not always, but sometimes. So this is used, there are many versions of Floer homology. It's used in two different areas of mathematics. The first one is symplectic geometry. In symplectic geometry, we have, for example, Hamiltonian Floer homology. This was the first one that was developed by Floer. And what is this? If we have a symplectic manifold M omega and some time-dependent Hamiltonian. So S1 is the time coordinate. Then we construct, we construct the Hamiltonian vector field like this. And from here, we get a flow, Hamiltonian flow, phi t on M. Okay, and yes, what is the Banach manifold that we associate with this setting? It's made of basically loops in M. We also need some capping of the loop typically. So yeah, so some disk, but this is defined up to equivalence. The loop is the important thing. Two caps are equivalent. So alpha hat and alpha hat prime. If you have two caps, you make a sphere, and we say that they're equivalent if if omega and C1 of Tm are both 0 on the sphere, on alpha, alpha prime. This allows us to define the area functional. It's given by, some formula, ht of alpha of t minus the integral over the disk of alpha star of omega. This is called the area functional. Yeah, and the critical points are the closed orbits of pi1, and the flow lines are pseudo-holomorphic cylinders in M. And from here you can define a Floer homology, which is called Hamiltonian Floer homology. And actually it turns out to be the same as the homology of M itself, but that's a non-trivial theorem. And using that, you can prove the Arnold conjecture. Well, maybe I should say it's defined in general with rational coefficients. There are various complications, but I'm just doing a survey, so this is the general idea. Okay, there is a similar construction when you have Lagrangians. So if M omega is symplectic and you have two Lagrangians, L0 and L1. So half-dimensional submanifolds where omega is 0. Then again, you can define, you can look at paths, this time gamma from 0, 1 to M, with gamma of 0 equals.
Here's what I found.
Oh, okay. Gamma of 0 is in L0 and gamma of 1 is in L1. So instead of being loops, you now talk about paths between the two Lagrangians. In good situations, again, you can define an area functional. And from here, you get some homology depending on L0 and L1, which is called Lagrangian Floer homology. Okay, and then there are others. There's something called periodic Floer homology, contact homology, and so on, but I won't get into them. All right, so these were the versions that appear in symplectic geometry. Now, the other main area of mathematics where we encounter Floer homology is low-dimensional topology. And there we have Floer homologies that are associated to three manifolds or to a pair made out of a three manifold and not, or a link. And from here you get some Floer homologies. And there are different versions. I will make a table. There are 6 main such theories. Okay, maybe I won't put the bottom line because I don't know where it will end up. The first one was again constructed by Floer. It's the instanton theory. It's based on the Yang-Mills equations. And there we have the 3 manifold, and the space B, the Banach manifolds, is made of SU2 connections on Y, modulo gauge, well, on a vector bundle over Y. And F is the Chern-Simons functional. So I don't know, your favorite normalization, then the trace of A wedge dA plus 2/3 A wedge A wedge A. Okay, that's one version. Now there is a something that it is equal to. There is an alternate construction of this from symplectic geometry. So symplectic instanton homology. This comes from splitting the manifold into a Heggard decomposition. So Y is the manifold, and you split it into 2 handle bodies along a surface. From here, you get some symplectic manifold M omega. It is the moduli space of bundles on sigma. And from each side, you get 2 Lagrangians, L0 and L1. Again, you can think of them as moduli spaces of flat connections. I won't tell you the details, but at this point, you apply the previous version, the one in symplectic geometry, the Lagrangian Floer homology, and you take HF of L0, L1. And, well, the Atiyah Floer conjecture tells you that these two are the same. And, well, it was proved in many cases by now. That's one theory. Another one is the monopole Floer homology, which is based on the Seiberg-Witten equations. Here B is made of pairs A and Phi, where A is now a U1 connection and Phi is a spinor from some spin C bundle over Y. And F is the Chern-Simons-Dirac functional. So it's something like, I don't know, minus A wedge dA plus integral of phi dA phi, something like that. And again, there is a Lagrangian version, which is called Heggard-Floer homology. It was developed by Urquhart and Szabo. Similarly, you split the 3 manifold into 2 pieces, and you associate some symplectic manifold to that. M is a moduli space of vortices, which are the reductions of the Seiberg-Witten equations, and it turns out to be a symmetric product. And you get some L0 and L1, and you can get this Heggard-Floer homology, which turns out to be the same as monopole Floer homology. But it's a different construction, and it's more easily computable. And finally, we have Khovanov homology. This is, originally it was not a Floer homology. It was defined combinatorially, and it's for knots in S3, but it's usually lumped together with Floer homologies because it has very similar properties. And in fact, it should be a Floer homology. So Witten conjectured that, well, there's a conjectural interpretation with gauge theory based on the 5-dimensional Hades-Witten equations. So at least conjecturally, it's a Floer theory as well. And again, there is a symplectic version of it, which is called symplectic Khovanov homology. And was developed by Seidel and Smith. Okay, so these are the three main versions. They all have various applications. They give different answers for the same knot. You can give different answers, or for the same three manifold. Yeah, and that's it. This was my quick review of Floer homology. Let's see, that was 1/3 of the talk. Great. Are there any questions?
Is it known that symplectic Khovanov homology comes from dimensionally reducing the Kapustin-Witten and Haydes-Witten equations in some straightforward way? Just like, because the other two relation that you mentioned.
Let me think for 1 second. I want to say yes. That's right. So you get some space of extended Bogomolny equations, and that is closely related to the Seidel-Smith space. Yes.
I see. Yeah, I think Greg has his hand up. He might have.
Yeah, go ahead, Greg.
So in the instanton case, there are natural generalizations where one replaces the instanton equations, self-dual instanton equations, the flow equation for Chern-Simons, by the non-abelian monopole equations, the non-abelian version of the Seiberg-Witten equations. Has anybody thought about that? So you could replace the SU2 by a general compact Lie group,
Maybe
and then take a quaternionic representation of that of that Lie group, and then you
yeah,
get
well,
natural generalization.
yes. Maybe your colleague Paul Feehan has thought about it, but I think right now, in principle, there should be something like this, but the compactness is much harder. And I think people are just studying the 4-dimensional versions. They haven't gotten to the 3D, like the analysis for Floer homology is harder than just for 4-dimensional manifolds.
Right, but you mentioned that the symplectic instanton was so much easier. So I was thinking if people found the analysis in that case so hard, what about the generalization on the symplectic side?
Oh, well, no, that even in the U1 case, it is hard. Like what do I want to say? So for example, in Hegardt Floer, we have this moduli space, like the symmetric product, which is sort of a moduli space of vortices, but not exactly. But L0 and L1 are just defined by hand from a Hegardt diagram, and people don't know if they are actually the spaces of Seiberg-Witten equations on the handle bodies, the moduli spaces from the handle bodies. So if you're trying to do this for non-abelian, then you would need some, you would need to write down M and L0 and L1, but you would have to write down L0 and L1 as moduli spaces because you wouldn't have such an easy description. And even the U1 case is not understood in that way. It's just understood from the diagrams. But I expect for the PU2, you would have to actually understand the moduli space of these PU2 monopoles on handle bodies.
I have another question. Is there any known conjectures about Khovanov homology, so some construction of Khovanov homology that uses Futer maps?
No, not that I know of.
Okay. Right. So
I'm not too familiar. I heard these words in combination with the work of Gaiotto and Witten, but yeah, I'm not too familiar with that.
okay, thanks.
Okay, Ciprian, go ahead. We'll have more questions.
Yes. Okay. So now let me go to Floer homotopy. Okay, so what is the goal? The goal is, given the same data as in Floer homology, like, for example, a symplectic manifold and a Hamiltonian, or two Lagrangians, or a 3-manifold, or a 3-manifold and a knot, we want to do more than a homology. Ideally, well, let me just say ideally, we want to construct a space X with the homology of X being Floer homology, and X should be invariant up to stable homotopy equivalence. I mean, the construction of Floer homology depends on some choices, like almost complex structures and like stuff like that. But in the end, you get a group well-defined up to canonical isomorphism. Similarly, here you would like to get a space well-defined up to stable homotopy equivalence. I'll say in a minute what that is in case you don't know. So X would be called the Floer stable, but we sometimes drop this adjective, homotopy type. So what is stable homotopy equivalence? It's homotopy equivalence up to suspension. If I have a space X, I can take its suspension, sigma X, by adding cones on X from two sides. And if I use the notation XY to be maps from X to Y up to homotopy, then stable homotopy would be stable homotopy classes of maps would be the co-limit as n goes to infinity of homotopy classes of maps between the suspensions, the n suspensions of X and Y. And starting from this, you can define stable homotopy equivalence, just a map in one direction such that, well, in this category, when you, yes, an isomorphism in the category of objects with stable equivalence classes. Okay, so this is ideally more generally, sometimes it's not a space, but X could be a spectrum in the sense of algebraic topology, i.e. a sequence of spaces Xn with maps Fn from sigma Xn to Xn plus 1. This is what people sometimes call a spectrum, sometimes a pre-spectrum. You can make a genuine spectrum out of it. I won't get into the details, but you know, instead of Xn being just the end suspension of some X as above, you can just take some other sequence of spaces with these maps and you get spectra. And there's a notion of stable homotopy equivalence of spectra. And there are even more general things like prospectra or twisted parametrized spectrum. Depending on your theory, you have to enlarge the type of algebraic topologic object that you hope to get. But in the simplest case, it's just a space. Okay, and what does this give you? So why do we want to do that? Well, if we have a Floer homotopy type as one of these gadgets, X, instead of taking its ordinary homology, we can take its generalized homology. So H star could be some generalized homology theory, like K theory, or KO theory, or Bordism, or stable homotopy groups. And these are theories that satisfy excision and Meyer-Vietoris and all that, but they take different values on the point. And they contain more info. They can contain more info than just the ordinary homology of X, which is Floer homology. Okay, so that is what we want. So let's see how to do it. So constructions. So the idea of Floer homotopy started with this paper of Cohen, Jones, and Siegel from 1995. And they proposed using a flow category. So what's that? So let's recall we're in the setting of a Banach manifold, and there's some functional on it. And well, we have a Floer complex, which is generated by the critical points of this functional, and the boundary map counts flow lines, gradient flow lines of this F. So from here, we're going to get a flow category, C, where the objects are the critical points, and the morphisms, so hum from X to Y, is actually a manifold, or a manifold with corners, is the compactification of the moduli space of flow lines from X to Y, unparametrized, and we want to include broken flow lines to make it compact. So these are broken flow lines from X to Y. And this is a manifold with corners. The boundary splits as the union over Z of M bar XZ times M bar ZY. Okay, okay, we construct this thing that's called the flow category. Now to get the Floer homotopy, we also need some additional data, namely framings. So we need framings, let me say, of the normal bundles of this M bar XY, stable normal bundle. So meaning when I put it in some big Euclidean space with corners, it has to be embedded so that it respects the corner structure. And I also want compatibility, like compatibility of these embeddings and framings with the relation for the boundary of M bar XY equals the union. So if everything is compatible and yes, and you have these framings, then you get what they call a framed flow category. And from here, they describe explicitly the procedure to get from here a space X, or a spectrum, really, depending if you put things in negative degree. But it's just, it's a suspension spectrum. Well, it depends. Actually, it depends. If you have infinitely many critical points, then it becomes a proof spectrum. Let me maybe just put in quotation marks space. It could be one of these more general objects. Okay, so how do you do that? I'll just tell you the idea. And this is simpler to explain when we have just two critical points. So let's say that the critical set is just 2 points, X and Y. And we're looking at flow lines between them. There's a manifold of flow lines. If these have some degrees, let's say these have degrees, X is in degree M plus K and Y is in degree M, then the dimension of M bar XY is K minus 1. If there are no other critical points, then this is already compact. We don't have to compactify it by any broken things. There's nothing broken. This is a smooth manifold. Maybe also frames. So we're assuming that we have framings. So now we're constructing a space. So X is going to be, well, we start with a base point. All our spaces are based. And then we add a cell for each critical point. So I'm going to add a cell in dimension M for X and one in dimension M plus K for Y. So this comes from X and this comes from Y. Together, this makes a sphere. And I want to attach this M plus K dimensional sphere. So I'm going to attach by a map tau from Sm plus K minus 1 to Sm, Well, this ends up being just, so this is an element, we can think of it as an element in the stable homotopy groups of spheres. So the thing is, in Floer theory, we don't really have absolute gradings. So we can make M, we can always just change our grading by some suspension. We can assume that M is very large, and then this is a stable map between Sm plus k minus 1 to Sm, and this is an element in the stable homotopy groups of spheres, which is just, sorry, let me try again. The other way. This is just bistable k minus 1 of S0, the k minus 1 group. And well, there is a well-known description of the stable homotopy groups of spheres by the Pontryagin Thom map. We can just consider framed k minus 1 dimensional manifolds, and we're taking this M bar xy. So this is going to be our tau. We just define the attaching map to be given by the moduli space of flow lines. And adding these cells using this map from the moduli space, we get our space X, and the homology is, well, if X and Y are apart by degree at least 2, then you just get two-dimensional homology. Okay, so this is the general idea, what should be done, but this is hard to do in practice. So this is, yeah, so in practice, this is not how people construct spectra, not quite. I mean, they have to work harder. So it's difficult because of several reasons, because we need, well, we need compatible smooth structures on these manifolds with corners. And these should exist, but just the analysis is hard, and it hasn't been done in many cases. Another issue is that we have, well, that's not what we need. That's, let me write it differently. Okay, this is because we need this, and also because we have bubbles. So the compactification, maybe I should give a name to this equation for what the boundary should be. It might not be quite true. So sometimes the spaces of flow lines, they don't converge. If you have a sequence, it doesn't converge to a broken flow line, it may bubble off. This happens in symplectic geometry and in Yang-Mills theory. And then, well, yes, star may not hold. That's a problem. And finally, framings may not exist. I didn't say where they come from. They have to come from your geometric situations, and sometimes they exist and sometimes they don't exist. Okay, all right. So let me tell you what is actually done in practice to construct the spectra and when it was done. So it was done in for some of the Floer homologies and not for others. So for example, for Hamiltonian Floer homology, this is the relatively recent work of Abouzaid and Blumberg from last year. Okay, then M bar xy are not quite manifolds, and they don't show anything about the smooth structure, but you can just work with them as topological orbifolds with corners, more or less. Have to discuss stuff like that. So there's some problem that they're not manifolds, they're orbifolds because of the bubbles. And you also don't want to deal with smooth structures. It's also suffice to think about the topological structure. And they're also not framed. yeah, so they have all the three above problem, but at least in this case, they're stably almost complex. So you can leave their structure group to U. So the framing issue is, in a sense, the most essential one, because you cannot define. So working with topological instead of smooth has to do with talking about the general smoothing theory and Kirby-Ziebenman and stuff like that. But well, topological manifolds also have tangent bundles, they have microbundles. So these are technical points, but the framing is a real issue. And you cannot expect to get a Floer homotopy type, but you still get something just from the stably almost complex structure, but we get complex oriented generalized, well, Floer homology theories. So instead of, just Floer homology, there are various generalized Floer homologies that you can get. They're the ones that are bundles over the spectrum MU. So the things you can get are things like K theory, but not KO theory, complex Bordism, and more importantly for their application, I'll get to that later, more what are called Morava K theories. So you can get more information, but you cannot get stable homotopy groups or KO theory. Okay, another thing that people can do in combinatorial situations, you can construct, so that's one option. You can construct a Floer, the framed flow category by hand, kind of inductively on dimensions. So that means without moduli spaces. And this can be done when you have a combinatorially defined theory. So from combinatorial data from a knot, you get some homotopy types. So you define this M bar XY. In this case, they're smooth manifolds with corners. There's no problem. And you get your Floer homotopy type. And this was done in two settings. It was done for Khovanov. So there's the Khovanov homotopy type of Lipschitz and Sharkar. From 2011. And it was done for knot Floer homology. So this is the version of knot Heggard-Floer homology. Again, this is just for knots in S3. So not in other three manifolds. There is a combinatorial definition of that, and working with that in joint work with Sharkar from last year, we defined a homotopy type in this case. So this doesn't involve any analysis. And finally, another thing is to bypass flow categories entirely and use finite dimensional approximation. So this works. So far, it was just done in Seiberg-Witten theory. Well, it was done in some settings in symplectic geometry as well. But let me just talk about this. So there is, I did this in 2001 for three manifolds with B1 equals 0. And then since then, there was various progress. I had a paper with Kronhammer. Then there was work of Handawit, Lin and Sasahira, and Staffragan, Sasahira, and Staffragan. And most recently, there's work in progress of Behrens, Hedenlund, and Krau. And this actually does it for all three manifolds. Yes, this is work in progress, basically. Yeah, okay, so how do we do it? I mean, there are some advantages. In Seiberg-Witten theory, we don't have any bubbles. And another advantage is that B is a Hilbert space. Let's say, at least when B1 equals 0, let's say. And it doesn't have any topology. It's not a Hilbert manifold. It's just a Hilbert space. And therefore, it's easy to approximate it by finite dimensional spaces. So let's recall in Seiberg-Witten Floer homology is about the Chern-Simons-Dirac functional. What we do is replace B by a sequence of spaces Bn in Bn plus 1 and so on in B. B is the completion of their union. And so Bn's are finite dimensional. And you restrict F to them. So you look at F restricted to Bn. Right, and then you are on a non-compact space, and that's why I started the talk by discussing Morse homology on a non-compact space. There we know that the Morse homology you get is the homology of something, and that something is the Conley index. So if we want a Floer homotopy, instead of taking the homology, we will just take the Conley index itself. So we take some Conley index associated to Bn, and then the sequence of spaces gives you a spectrum Xn. This is the Seiberg-Witten Floer stable homotopy type. Yeah, so this doesn't use any flow categories. All right, so as far as I know, these are the three things that, the three major techniques for producing Floer homotopy types. Greg, do you have a question, or is your...
Yes. Is this related to the Bauer-Ferrutta invariant?
Yeah, absolutely. So when, I mean, just like Seiberg-Witten invariants, when you cut the four manifold in pieces, you get gluing formulas in Floer homology. Well, if you want to compute the Bauer-Ferrutta invariant, you cut your manifold in pieces and you pair some relative invariants that that are basically maps from the sphere to the Floer homotopy type.
Thank you.
Okay, so all right, so we discussed the ways of constructing it. So again, it was done in Hamiltonian Floer homology. Maybe I should go back for a second and just review when such things exist and when they don't exist. So this is sort of done. This means there exists some Floer homotopy type, not quite. There is just something weaker that allows you to do some generalized homology theories, but that's the best you can possibly hope to get. I mean, just because of the framings. In Lagrangian Floer homology, this is still needed. Maybe I should say it's work in progress also by Abouzaid and Blumberg. They're trying to do this. Then in here, we have it in monopole Floer homology. We have it in Khovanov homology. And we have it for knots in Hegat Floer homology. But we still need to do it in Hegat Floer homology in general, in symplectic Khovanov homology, in symplectic instanton, and in instanton. So there is still work to be done.
How many of those Floer homology theories have a combinatorial description?
That's a good question. The last two, so Hegat Floer and Khovanov, yes, and instanton it doesn't. Okay, so now why do we want Floer homotopy? Well, it gives us more information than Floer homology, and sometimes you get applications out of it. I will just mention two of them very briefly. So the first one is a theorem I proved in 2013, that there exist non-triangulable manifolds in each dimension greater or equal than 5. Previously, it was known in dimension 4 by the work of Casson from the 80s, based on the work of Mike Friedman. And well, what does this have to do with Floer homotopy? Where in the 70s, Galuski, Stern, and Matsumoto in the 70s reduced this problem to a question in 3+1 dimensions instead of high dimensions. They wanted to show that there is no three-manifold, well, an element in homology cobordism that is 2 torsion and mu of y equals 1. I will say in a moment what these are. So theta 3z is the homology cobordism group, is generated by 3 manifolds with the homology of S3 modulo an equivalence relation when they co-bound a 4 manifold with trivial relative homology. This forms a group, theta 3z, and there is a well-known Rachlin homomorphism to Zima 2. So this is what Galuski-Stern conjectured, and I showed, and this implies the theorem. So the way you show this is from Y. I'll be very brief. You look at the Seiberg-Witten equations on Y, and you notice that they have a symmetry by the group ping 2. And well, and you construct the Seiberg-Witten Floer homology, which is ping 2 equivariant. So this is just ping 2 equivariant Floer homology. Okay, so you just need homology, but you need it to be equivariant. And it's hard to construct equivariant theories using just Morse complexes. So it turned out to be much helpful to have the Floer homotopy. So the idea was to take the Floer homotopy X, and then, which is defined with this finite dimensional approximation, and then take the ping 2 equivariant, just Borel homology of this X. So that's, in a sense, the easiest way to define, to put equivariance into Floer homology by using homotopy. Once you have this group, well, there's a whole story, but you construct some lift of theta 3z to z, of the mu invariant of the Rachlin to z, such that beta of minus y is minus beta of y. This is some invariant that you extract from this ping 2 equivariant homology. And now you show that if you had a torsion element, then you would get, well, then beta of minus y. We know that it's minus beta of y, but it's also beta of y, because y is minus y in homology cobordism. From here, you get that beta of y is 0. And since it's a lift of mu, you get that mu of y is 0, which contradicts that mu of y is 1. Okay, so there are many details. For reasons of time, I'll just tell you this sketch. But the important thing is that you can include equivariance in your theory very easily once you have a space. And the same idea was used in Khovanov homology for other purposes, for constructing equivariant theories. Right, that's one application. I have 5 minutes for another application. This is the Arnold conjecture mod P. And this was proved by Abouzaid and Blumberg in last year, 2021. So let's recall that we had Hamiltonian Floer homology. We have M omega and some Hamiltonians. We get this HF, and in general, this is only defined over the rational numbers because of bubbles. But we know that it is, well, with rational numbers, we know that it's the same as the homology of M itself. And we know that the Floer complex is generated by roughly closed orbits of the time one flow, Hamiltonian flow. And from here, you basically get a proof of the Arnold conjecture, well, assuming you constructed Hamiltonian Floer homology, which was a big thing due to many authors, Floer, Fukaya, Ono, Salomon, Hofer, Fukaya, Taono, and and other people, maybe Ruan. But in the end, you get that the number of closed orbits is greater or equal than the rank of the homology, well, maybe I should just say dimension of the homology of M with rational coefficients. So this was known before, but what Abouzaid and Blumberg do, they define more than homology, they define complex-oriented generalized Floer homology in this case. And the one that they care about is Morava K-theory. This is something that was known in homotopy theory. It's some theory that it's associated to a prime and some integer. It's called KPN. And they construct HF, well, their notation is something like HF of M. Well, I guess it depends on the Hamiltonian, and it also depends on this KPN. Like these are the coefficients in the sense of the homology. It's the spectrum over which is defined. And it's defined over the Morava K-theory of a point as a module, which is the field of P elements adjoined some variable V of degree 2Pn minus 1. And the thing about this is that there's an Atiyah-Hirzebruch spectral sequence. You can show that this is the same as the homology of M with Fp coefficients for very large n, because this degree of V is very large when n is very large. Okay, and this is defined again using just closed orbits, and what you get from here is that the number of closed orbits is greater or equal than the dimension of of the homology or cohomology of M with Fp coefficients, which is a different result. It's a stronger result than just with rational coefficients. So this is the Arnold conjecture mod P. Okay, I will stop here.
Great. Well, let's thank Ciprian for a beautiful talk. So please raise your hand if you have a question. We've had a lot of questions and discussion, but if there are any remaining questions at this point. Well, okay, then I'll ask Ciprian, what are the kind of biggest open problems or new directions that people are thinking about?
Yes, well, defining these things for the theories where we haven't defined. So I understand Abouzaid and Blumberg are trying to define Lagrangian Floer homotopy and spectral Fukaya categories associated to symplectic manifolds. I think we're in, we should have the tools to define an instanton Floer homotopy, but it will still have the issue of bubbles, so you will only have the complex-oriented theories. And yes, I'm working with Abouzaid on Hegardt-Floer homotopy for 3 manifolds rather than knots. And there are people, well, and there are people exploring the applications of these theories.
Okay. Hassan, go ahead.
Yeah, I'm just wondering if there's a quantum field theory reason to expect this more refined structure than just ordinary Floer homology.
Oh, that's a great question. I don't know. Does anybody else know?
Well, that's why I asked about Bauer-Ferrute. It's really not too clear what the physical interpretation of the Bauer-Ferrute invariant is.
Yeah, I mean, you can formulate the thing mathematically like a spectral TQFT. Instead of numbers, you have maps between spheres, and instead of homology groups, you have spectra, and then you have maps between spectra. So you can formulate, spectral TQFT, but I don't know about the connection to physics.
Cool. Yeah, thank you.
Other questions? Okay, if not, let's thank Ciprian again. And the next talk in this series will be in 2 weeks. On October 17th, it'll be Mike Douglas from CMSA. So hope to see you then. Thanks.
Thanks for having me.
Thank you, Ciprian. Did I stop? There we go. Everyone disappeared.